Welcome to Lecture 25 on curve sketching. We're going to combine the ideas from the previous lectures in order to sketch a more complete picture of functions. So here I'm going to list a bunch of things that you want to keep in mind. This is not completely exhaustive, but here's a list of things that you want to be looking for in order to prepare yourself to sketch the graph of a curve. So I'll list some of them over here. So one thing you might want to do is you might want to find the x and y intercepts for the graph. And depending on what the function is, that may be easy or that may be quite complicated. But remember, for an x-intercept, you're looking for a point x1, 0. And then for a y-intercept, you're looking for a point 0, y1. So setting the other variable to 0. So you might want to look for these points. They might help you begin to draw the graph. Another thing is to find critical points. So we've done that in some of the previous lectures now. And remember, this is where you have f prime of x equals 0, or f prime of x is undefined. And we search for these critical points because around these critical points, the graph might behave differently. It just depends on what we're talking about. These critical points are important. Another thing you might want to keep in mind is we want to find the intervals of increase and decrease. And that was using the first derivative. Remember, if the first derivative is positive, you're increasing on that interval. And if the first derivative is negative, the function is decreasing on that interval. And then similarly, we'd like to find the inflection points and where f of x is concave up or concave down. And remember, this stuff involved looking at the second derivative. And if you were positive for the second derivative, you know the graph is concave up. And then you know it's concave down when the second derivative is negative. And then here's one more thing I'll suggest. So you could find the vertical and or horizontal asymptotes. And depending on the function, these might not even exist. You could have at most 2 horizontal asymptotes. You could have very, very many vertical asymptotes. You could have infinitely many. But these may apply to your graph as well. It might be worth it to search for these as well to help you get the shape of the graph. All right, let's look at an example here. I'm going to start easy, and then I'm going to do 2 examples that are going to be a little more complicated. Let's start with this one. Knowing the parent function and knowing what functions look like in general is very helpful. This is a polynomial, so we know that the domain for this is going to be all real numbers. We know this is a nice continuous function, so knowing ahead of time that it's a polynomial, it's going to be some kind of polynomial curve, is good. Let's start looking for some of the things that I listed over here. So if you wanted to look for x and y intercepts, one thing that's pretty helpful is we know that f of 0 is 0. So when I do begin drawing my graph, I know I'll have a point at 0, 0. That was very easy for me to find. Let's continue from here. What I'm going to do now is I'm going to take the first derivative. There's really no set order you have to do these things in, but the more of these that you have, the better equipped you're going to be for drawing the graph. So if I have the first derivative, it's going to be 3x squared minus 6x plus 3. And I'm going to go ahead and set this equal to 0 because I'm looking for the critical points. So I'll say we're going to find the critical points. So that means I'm going to take the first derivative, and I'm going to set it equal to 0. Notice that I could divide every term by 3, and that's OK. So I could simplify this to x squared minus 2x plus 1 equals 0. And then this factors into x minus 1 squared equals 0. So x equals 1 is a critical point. So I might want to look at what's happening with the first derivative around 1. We get no critical points where the first derivative is undefined because it's never undefined. This is a polynomial. Its derivative is a polynomial. So this is our only critical point. It's very helpful to look at what's happening here. So I have 1. Let's test around this in the first derivative. So we'll test 0 and 2. So if you plug 0 into the first derivative, what type of number do you get? You get a positive, which means we're increasing from negative infinity to 1. And then if I plug in 2 into the first derivative, so I could use this right here. I can plug in 2 into the first derivative of my factor one. You notice this is also a positive number. So we're increasing from 1 to infinity. So what this means is we didn't get any kind of like sign change, so we're increasing on the entire domain. So this function is always increasing. That's good to know when we're drawing the picture. So f of x is always increasing. That's great to know ahead of time. Okay, so let's move on from there. Let's look at the second derivative now, because the second derivative gives us a little more information about the shape of the graph. So taking my second derivative, I'll start from up here. So I'll get 6x minus 6. And I'd like to find if the concavity changes. So I'll set this equal to 0. So what we're doing now is we're looking for inflection points. So let's search for those. I'm going to set this equal to 0, which means 6x minus 6 is 0. So 6x equals 6, or x equals 1. Interesting that there's also something here at 1 as well. So this could potentially be a point of inflection. I need to check and make sure the second derivative changes here. But this is where the second derivative equals 0. So something could be going on here. So let's plug in 1 here. I'm going to test the two numbers from before, 0 on the left and 2 on the right. These are going to get tested into the second derivative. So plug 0 into the second derivative, I get negative 6. So this means this is negative. In other words, we're concave down from negative infinity to 1. If you plug in positive 2 into the second derivative I have here, this is going to be a positive 6. It's a positive number. So we're concave up. This is from 1 to infinity. So actually, from examining this, we have 1 comma, and then I would need to go find the original y value. So let's go do that in the original. So if you go way up here, I have 1 minus 3 plus 3 is going to be 1. So 1, 1 is an inflection point. So our graph is going to intersect the point 1, 1. And at that point 1, 1, it switches from concave down to concave up. OK. I'm trying to plan in my head now where I'm going to draw the graph. I see this nice space here. I'm going to reserve this for our graph right now. I don't want to lose this real estate. So let me take this. Let me draw a couple things that I know already that I could easily put on the graph. We have the point 0, 0. So I'm going to graph that right now. I know that's true. What else do I know? Well, let me put a few markings here. These are going to be counted by 1s. I have the point 1, 1, and it's an inflection point. So let me graph that. OK, let's continue here. So what else might I want to look for? Well, there's no vertical or horizontal asymptotes. So no vertical asymptotes and no horizontal asymptotes. So we're good there. That's because this is a polynomial. We're defined for all real numbers. We don't have any kind of asymptotes happening here. But one thing I do want to say is that the limit as x goes to infinity of f of x and the limit as x goes to negative infinity of f of x. These will tell us where our graph ends up going. So we have an x to the third power. So plugging in a very large number for x, this power kind of, or this term sort of dominates what's going on. And this is going to go to infinity. Here I have an odd power. So if I plug in -1 here, and then also plug in a large number, this will go to negative infinity. So we kind of have tail behavior where it's going up on the right, and then if you go out left, it's going to be down. So we have something like this. We have a tail that goes this way. We have a tail that goes this way. Okay, I need to be concave down from negative infinity to 1. Okay, so I'm going to do that. I also need to make sure I'm increasing the entire time I'm drawing this graph. So this should always be increasing. Okay, so I'm increasing, and then I switch to concave up right here from 1 to infinity. So I'm going to now switch to concave up. If you wanted to even fine-tune this more, there's nothing stopping you from picking a couple points that you'd be interested in. So for example, f of 2, if you were to plug that into the original, you would get 8 minus 12 plus 6. I believe that's 2. So 8 minus 12 would be -4, plus 6 would be 2 exactly. So you would have the point 22. And similarly, if you wanted to know something maybe on the left side, you could plug in -1. And for that, I believe I got -7. So this is our graph. It accounts for the concavity. It accounts for this point of inflection right here at 1, 1. Accounts for it always increasing. We have a nice cubic graph, which is what we'd expect ahead of time if we had this polynomial. Okay, so that was kind of our introductory example. I'm going to do 2 more examples as soon as I erase all this stuff. So I'll see you in just a moment. So now I have 2 more examples that we're going to go over. So the first one is to sketch the graph for e to the x over x. And I've already rewritten this as x to the -1 power because we can do that. And my plan for doing that was to do a product rule instead of doing a quotient rule. So that's why I've rewritten it. So let's consider what the domain of this is first. So our domain is going to be all real numbers, except for there's one number you're not allowed to plug in, and it's 0. So just make sure we do not include 0. It turns out, because we cannot make the denominator 0, we have a vertical asymptote at x equals 0. So we'll need to include that in the picture. In fact, I guess I'll go ahead and do it right now because I know that we're stuck with that. So right here, I'll draw this dotted line right there. It's kind of hard to see, but I tried using a different color. Let's go ahead and start now with the first derivative. So we're going to take the first derivative, and I'm going to use the product rule. So product rule on this, derivative of the first is -x to the -2. E to the x plus, I'm going to leave the first one alone. Derivative of e to the x is e to the x. And what I'm doing right now is I'm going to find the critical points. This is how we're going to test where the function is increasing and decreasing. So first I'm going to factor this. The smallest power of x I see is to the -2. So to factor this, I'm going to write it like this. It's going to be x to the -2 times. Factoring this, I get -e to the x. -1 minus -2 gives me a +1 for the power. Now, I've just also noticed that they both have e to the x in common. I probably should have seen that earlier. So I'll factor that out as well. So I'm going to get x to the -2 times e to the x times, I'm going to switch the order of this because I don't like the minus signs first. So we're going to get x minus 1. And I'm going to set this equal to 0. So the question is, can I get any of these to equal 0? Well, this one right here I can. So x equals 1 is a critical point, because that'll make the first derivative 0. Are there any other ones? Well, if you look at this factor, e to the x is always greater than 0 for any real x here. So e to the x will not equal 0 anywhere, so this will not give us anything. Remember, x to the negative 2 is 1 over x squared. So that's not going to equal 0 for any real x either. So my only solution here is going to be x equals 1 as a critical point. Now, does the first derivative go undefined? The answer to that is yes, because you can't plug in 0 here. However, it's not a critical point because it never belonged to the original domain in the first place. So x equals 0 is not a critical point. So this is our only one. Let's use this and test what's going on. So just like the other problem, mysteriously, this is 1 that I'm testing around for the first derivative. It is just coincidence. I'm going to plug in test values. I'll plug in 0. I'll plug in 2. If we go to the first derivative, I like this factored form here. So notice that, I'm going to use a different color for this part. Notice that of my 3 factors here, here, and here, this one is always positive because I have 1 over x squared. E to the x is always going to be positive, no matter what type of real number I plug into there. And then this is the only factor that I'm not sure of. So if I plug in 2, I'll get a positive. So all of these will be positive. And we're increasing from 1 to infinity. And if you were to plug in 0 right here, we'll have positive, positive, negative. So this is going to be negative, which means we're decreasing from negative infinity to 1. OK, so we know where we're increasing and decreasing. We know here we have a special type of point. So if we're going from decreasing to then increasing, we have 1 comma something is a local. And then what would that be? If I went from decreasing to increasing, this is a local minimum. If I can get the actual value here too, that would be great. So if I plug in 1 into the original, I just get e. So for sure, that's a point on the graph, and it's a local minimum. So if I'm going to go to 1, e is about 2.7, so I'm going to go like about here. And I know I have a local min, so I'm going to give it kind of like a rounded, like this, kind of just to show that this is going to be a minimum, just to remind myself. OK, let's continue. So now that we have the first derivative, let's rewrite this. So I'm going to rewrite this as f prime of x is, I'll take this x to the negative 2 power and actually distribute this back in to this third term. So I get e to the x times x to the negative 1 minus x to the negative 2. So I'm rewriting the first derivative just to make my second derivative easier. I kind of see that I went off screen a little bit. All I wrote here was f prime of x, but I'll try to squish it in here a little better. OK, so this thing right here is what I've rewritten as f prime of x. Let's go ahead and take another derivative. So f double prime of x. Keep the first one the same. This is the product rule. These are the 2 functions I'm using the product rule for. So keep e to the x the same. Derivative of this is going to be negative 1x to the negative 2 plus 2x to the negative 3. So that was the first half of my product rule. I'm going to do plus, switch the order. Derivative of e to the x is e to the x. Leave the second factor alone now. OK, so that's my second derivative. I'm going to go ahead and, I guess I'm going to go ahead and try to FOIL things out here. So I'm going to have negative e to the x, x to the negative 2. Plus 2e to the x, x to the negative 3, plus, I'm distributing the bottom one here now, so I have e to the x, x to the negative 1, minus e to the x, x to the negative 2. So all in all, I can combine these two. And if I kind of reorder this, I'm going to get e to the x, x to the negative 1, minus 2e to the x, x to the negative 2, plus 2e to the x, x to the negative 3. So this is what my second derivative looks like. I'm going to factor out the largest power, or sorry, the smallest power of x that I see in everything again, just like I did before. So this is equal to e to the x. The smallest power of x I see is x to the negative 3. This would leave me with x squared here. This would leave me with minus 2x. And then for this last term, I'd have plus 2, and I factored out e to the x, x to the negative 3. I'm going to set this equal to 0, because I want to see if there's any kind of change in concavity here. So I have this. I'm asking myself, will this ever equal 0? Okay, so you'll find here that there are no solutions to this, because this has all imaginary roots, and e to the x will be a positive number, and 1 over x cubed, so this right here, you will never be able to make that equal to 0 for a real number x. So where do I test for concave up, concave down? Well, there is one value where the second derivative goes undefined, so we do need to check around there. So let me place 0 here. The thing is, though, is 0 will never belong in the original domain. So I'm not going to have a point of inflection here, per se, because that's not actually defined in the original. But we could check here to see if there's some kind of concavity change anyway. So I can plug in 1 as a test value, and I can plug in negative 1. So if you plug in 1 into my second derivative here, e to the 1 is positive, 1 to the negative 3 is positive. And if I look at this here, I have 1 minus 2 is minus 1 plus 2 is positive. So here we're concave up. And if you were to test negative 1 into this second derivative here, you would find that this is negative. So here we're concave down. So even though you had a change in concavity, you don't have the inflection point at 0 because you can't plug it into the original. So there is no point where it changes inflection. You do just have different concavity on either side of this. It's because you have this asymptote here at 0. Okay, can we put all this together to form some kind of coherent graph? There's a couple more things I really need to know. So first thing I want to know is what happens around this asymptote? Well, to figure that out, we can go back to lecture or exam 1 stuff. We could take the limit as x goes to 0 on the right side of f of x. If you plug in a very small positive number into up here, you'll see that the denominator is approaching 0, so we're going to get some kind of infinity. And the top here is going to be positive. So a positive over a positive gives me positive infinity. And not only that, but I know I'm concave up from 0 to infinity. And let me write that a little better over here. From 0 to infinity. So I know the graph goes something like this. How about on the left side? So you take the limit as x goes to 0 on the left of f of x. We get a sign change because if I plug in a very small number on the left, you're going to have a negative number in the denominator. So let me write that a little closer so it's on the screen. So you have a negative number on the bottom and still a positive number for e to the x. So what's going to happen here is you get negative infinity for the limit as x goes to 0 on the right. So we're going to get something to this effect right here. Whereas you're approaching 0 on the left, you go to negative infinity. What else do I know about this graph? I know we're concave down from negative infinity to 0. So this is going to stay concave down. And also, I know we stay concave up on this whole piece. It might be worth it to plot a couple other points. You could do that. We didn't talk about finding the horizontal asymptote, so maybe there's something there for us. So let's do that. So we need to consider 2. This is the limit as x goes to infinity of f of x. So for this, I'm going to ask myself the question, which one of these things grows faster? E to the x grows much faster than x. So if I compare these two, the numerator is much larger, so this limit's going to be infinity. If I do the limit as x goes to negative infinity of f of x, that's the same thing as plugging in a negative, so a negative 1, and then just evaluating the limit as x goes to infinity. So if I plug in the negative, I get e to the negative x over negative x. Well, what is this going to be if I can fit this right here? So e to the negative x goes to the denominator. So just like this, I get 1 over e to the positive x now times x in the denominator. So I have a fixed 1 in the numerator. What happens when I have 1 over an extremely large number here, or extremely large negative number? This will go to 0. So I have a horizontal asymptote at 0 as I go to the left, and I have a horizontal asymptote to, I don't really have one, but I have the behavior of the graph goes to infinity on the right. So here's my final picture. So as I go to the left, I stay concave down, and I approach 0 on the left here. And then on the right, I'm going to go up to infinity forever. OK, so this is the graph of this. We used lots of different pieces of information, and we can double check and make sure that I was decreasing on the correct interval. From here to 1, I'm decreasing, which matches with this, and I'm increasing from 1 to infinity. And again, if you need a little bit more detail, you can always plug in 1 or 2 more points just to guide you as well on those gaps that you're missing. All right, let's take a look at this final example here. So I'm going to sketch this graph of 2 square root of x minus x, and I've rewritten it again just to make the derivative easier for myself. Are there easy points that I can grab? Sure. If you plug in 0, you do get 0. So that's a point on the graph. So maybe one thing I should mention is that the domain of this one is different. The domain is x needs to be at least 0, because you cannot plug in a negative number for this radical. So that's something to keep in mind. I have the point 0, 0, so I could go ahead and plot that here now. Are there any other easy points I could grab? Well, maybe I can find another x-intercept. So let's try to find all the x-intercepts. How do you do that? You set y equal to 0. So I'm going to have 0 equals 2 root x minus x. If I add x to this side, I'll get x equals 2 root x. You can square both sides, and you'll get x squared equals. What happens if you square this? You square each piece, so I'll get 4x. Let's subtract the 4x over, set it equal to 0, and then factor. So I'll get x times x minus 4 equals 0. Then it turns out x equals 4 is another intercept. And if you plug in 4, you'll get 4 minus 4 is 0. So that's another point on our graph that would be good to have. So f of 4 is 0. So right here, 1, 2, 3, 4, I'll go over to 4 and plot another point. It's a good start. Let's get the derivative, though, just to see if we can find out more about this graph. If I take the derivative of this, it's going to be x to the negative 1/2 minus 1. I want the critical points. So we're going to set this equal to 0. How would I solve that? I could add 1 to the other side. And then I could raise both sides to the negative 2 power, so maybe something like this. And I'll get x equals 1 to any power is going to be 1. So x equals 1, mysteriously again, is a critical point. Let's keep looking at this. So this first derivative is the same thing as 1 over the square root of x minus 1. I'm showing that because the first derivative also goes undefined at 0, which means x equals 0 is a critical point as well. It's not going to be so useful, though, because that's kind of where our domain ends on the left. 0 is the last number I can plug in on the left. So it's good to point out that it's a critical point, but I don't know if it's going to really help us too much. Because if I'm doing my interval testing now, 0 is the place where I would stop The graph doesn't exist over here because the domain needs to be everything larger than 0 or including. So you just have these two pieces to test around. And we're going to test this in the first derivative. So if you plug in, let's say this will be a half, and this one will be 2. Those are our test values. Plug in a half into the first derivative. So which one do I want to use? Maybe this one. So if you plug in a half here, you're going to get a positive. I'm going to get 1 over root 2, which will be root 2. So you can take a moment to look at that, but that's positive. So this is increasing. We're going to be increasing from 0 to 1. If you plug in 2, you get 1 over root 2. That's a number smaller than 1. Minus 1 would give us a negative here. So we're decreasing from 1 to infinity. Good to know. 1 is defined in the original graph. So if we're going from increasing to decreasing, I'm kind of sensing I want to change colors again. If we're going from increasing to decreasing, what type of thing happens here? This is a local max at the point 1 comma something. I've got to find out what it is. So if you plug in 1 into the original, you get 2 minus 1 is 1. So we've got a local max at 1, 1. That's a point on my graph. I'm going to take it. So I know that's on my graph. I also know it's a local max. So everything around it is going to be lower. So I'm going to kind of draw some kind of like suggestive thing here to say that that's like a max there. Let's do concavity. Let's go ahead and do one more derivative. I'm going to start with this one. So f prime of x equals x to the negative 1/2 minus 1. The second derivative from here is not so bad to compute. I'll do another power rule. It'll be negative 1/2 x to the negative 3/2. Derivative of minus 1 is just 0. I really want to rewrite that. That doesn't look like something I can really think about. So if I have something to the negative power, I have x to the positive power if I move it to the denominator. So this is my second derivative. Can I ever make this equal to 0? No. I have negative 1 stuck up top here. The way you make a fraction equal to 0 is if you set the numerator equal to 0, but that's not possible. I also want to ask the question, where does this go undefined? And there is one value where it goes undefined. So f double prime of x is undefined at x equals 0. However, that's also not really going to give us much information because remember, to the left of 0, we don't care about the function. It isn't defined. So I don't really create any test intervals. I just have this one interval that I need to pick some kind of number. I'll just pick 1 because it's the easiest to test. So if I take this 1 and I go to the first or the second derivative here, I get negative 1/2 times 1. This is negative. So no matter what number I pick in here, this is going to be negative. So I know we're concave down. And that's from 0 to infinity. So that's good. I mean, I know the whole graph is going to be concave down. I've got this nice local max here. Here's my picture. I'm always concave down. One thing to point is there's no vertical asymptotes per se. It's just the graph kind of stops right here at x equals 0. So yeah, that's my picture of the last one right there. So I feel like this one wasn't so cumbersome with the derivatives. All right, I hope this was a great start in helping you sketch graphs. Go try your lecture quiz, and until next time, I'll see you. Please reach out to me if you have any questions by email. See ya.